Today we're going to be talking about growing Clojure via InferenceQL synthetic data generators. First, a little bit about us. My name is Zane, and I'm InferenceQL's engineering lead. Uli is our product and probabilistic programming lead. And Vikash, who will be helping me out with this talk, is the principal investigator of the MIT Probabilistic Computing Project. Here's an outline of what we're going to be covering. First, I'll share a personal view on growing the Clojure community. Then Vikash will give you an overview of InferenceQL, a probabilistic programming platform implemented in Clojure. Then I'll cover generating synthetic data using InferenceQL and customizing InferenceQL's automatically synthesized programs. Finally, we'll talk about how Clojure has helped InferenceQL grow and how we hope to grow the Clojure community. Recently, Clojure celebrated its 15th anniversary, and Nubank held a panel to celebrate where Rich Hickey, the creator of Clojure, was asked whether he saw an area of computing that would particularly benefit from Clojure's strengths. And he said that Clojure could be a great data science language. We totally agree. It's one of the reasons why we chose to implement InferenceQL in Clojure in the first place. There's been a lot of activity in data science in terms of libraries, with new libraries being created and awesome features being added to existing libraries. In particular, we've gotten a lot of benefit from libpython CLJ and tablecloth in our work on InferenceQL, and we're grateful to their maintainers and contributors for their hard work. It'll be interesting to see which killer capabilities from these libraries wind up driving the adoption of Clojure for people who are doing work in data science. But in this talk, we want to talk about a complementary bet on Clojure for data infrastructure. We believe that there's two global trends that are making it increasingly difficult to use and share data safely. The first is the rise of remote work, which skyrocketed during the pandemic and remains high today. This means that an increasingly large share of people who work with data are doing that work somewhere other than the office. And this new way of working isn't going anywhere. A majority of people surveyed who worked remotely during the pandemic said they would rather quit than return to the office. The second trend is the rise of privacy legislation, both at the state level in the United States and worldwide. In 2021, 29 states introduced privacy bills, 23 states held committee hearings, 7 states passed bills in one chamber, and 2 states passed new laws. So there's a tidal wave of new legislation that's passing through state legislatures as we speak. The situation is similar at the international level. A recent study predicted that privacy laws will regulate the vast majority of worldwide consumers by 2023. Consider the following scenario. You're a software engineer, writing Clojure, of course, working remotely from a beach in Bali for a company that's based in California in the United States that writes financial transaction processing software that processes transactions between the European Union and Australia. The data you need to access to do your job is governed by an alphabet soup of privacy laws, the CCPA, the APA, and the GDPR, at least. And the consequences for running afoul of any one of these laws can be quite expensive. Businesses are increasingly going to be looking for ways to mitigate this risk. We think that InferenceQL can solve this problem, and that we can use this business need to help fund the adoption of Clojure in the enterprise.
Let me show you what InferenceQL is using the problem of replacing sensitive data with safer synthetic data generators that are also easy to audit and customize. InferenceQL makes it as straightforward to query from a synthetic data generator, let's say via SQL Select, as it is to query original real data. This graph is showing the accuracy of machine learning models trained using this approach. The y-axis is error, so lower is better. We can see that machine learning models trained on the real data have some error, and the error when they're trained on synthetic data generated from InferenceQL is higher but significantly lower relative to baselines from a methodology that's in use at major investment banks and from a neural network approach that's from an active synthetic data startup. To get a qualitative feeling for the differences, here we're showing InferenceQL's synthetic data in orange overlaid on real data on the left. And on the middle and right, we're showing two different statistical modeling approaches, one based on copula models and one based on neural networks from an open source platform that's also the basis of an active synthetic data startup. And we can see the InferenceQL approach produces synthetic data that's qualitatively more accurate and matches both clusters where real data is likely and some of the dispersion in regions where data is unlikely but still possible, whereas the other approaches exhibit systematic biases. InferenceQL is the basis of over a decade of research on probabilistic programming and automated Bayesian inference at MIT. That's also been the basis of two successful venture-backed startups that became part of Salesforce and Tableau, respectively. I won't go into the details of this research here, but the high-level picture is that in InferenceQL, you learn probabilistic programs from data and then query them using a SQL-like interface that can make predictions, infer probable anomalies, and generate synthetic data. And the references on this slide show some of the computer science and computational statistics problems that we had to solve to scale Bayesian structure learning and probabilistic programming to this challenging setting. Here, what we're showing is a visualization of how InferenceQL learns probabilistic programs from data. Tabular data is streaming in on the right, and on the left, we're seeing a visual representation of uncertainty over the structure of learned probabilistic programs at several different levels, from which probabilistic programs are used to how rows are clustered and what parameters are involved. Later, Zane will show you a Clojure representation of these probabilistic programs, so you can see all the details of how InferenceQL is modeling data and generating accurate synthetic data. Over the years, we've found that InferenceQL can generate realistic synthetic data from a surprisingly broad range of databases, including oncology clinical trials from a major pharmaceutical company, whole genome RNA sequencing data from the MIT Harvard Broad Institute, a survey of software developer salaries from Stack Overflow, which you'll hear more about later from Zane, and data at multiple scales from the US Census. This data varies from just hundreds to many thousands of rows and just 10 to several thousand columns. So data of a broad range of scales can be modeled accurately using InferenceQL.
In each of these examples, the real data is in one color and synthetic data is in another color. As you can see, the synthetic data is generated quite accurately. Now I'll walk you through using InferenceQL's query language to generate some synthetic data. InferenceQL extends a subset of SQL with new language constructs like this generate expression. This expression returns an infinite table of synthetic data. The data generator we're using here was synthesized from the 2021 Stack Overflow Developer Survey, so what we're going to get back when we query it is synthetic survey responses. Because the return table is infinite, if we were to execute this query as written, it would run forever. But we can limit the number of rows generated by using SQL to select from it with a limit just as we might any other table. The generate expression could be thought of as producing a new infinite table of synthetic data every time it's evaluated. So if we were to execute this query again, we would get a different set of results. Now let's explore generating synthetic data subject to constraints. Here are three queries. The first generates survey responses without any constraints. The second generates survey responses from women. And the last generates survey responses from non-binary people. Below each query is a scatter plot showing data returned by selecting from the real table in black, and data returned by selecting from the synthetic table produced by the data generator in orange. On the y-axis, we have salaries in US dollars, and on the x-axis, we have years coding professionally. InferenceQL is able to generate realistic data even when subject to these constraints. Note that women and non-binary people who answered the survey were less likely to make very high salaries, regardless of how many years of professional experience they had. I'll touch on that again a bit later. Now, the data scientists in the audience might be wondering, why not just use bootstrapping? Couldn't we write a good enough synthetic data generator by randomly sampling from the source data and adding noise? Here's a Clojure program that sketches out that approach. We add noise to numerical values by adding or subtracting some small randomly chosen number. And then we add noise to categorical values by randomly selecting a different category some small percentage of the time. Now, I'm no data scientist, but I can see some data science challenges to this approach. Firstly, these kinds of programs are very hard to tune. How much noise should we add? If we add too little, we'll expose the source data, and if we add too much, we'll destroy the signal. But the real showstopper here is that we've included the real data in the generative program. This defeats the whole purpose of the exercise by making the generative program only as portable and shareable as the real data was in the first place. Let's take a closer look at one of the probabilistic programs that generated the survey response data that we saw earlier. We can see that it first randomly chooses one of 3 clusters, and then based on the cluster chosen, it samples values for salary and gender from one of 3 pairs of distributions. Those values are then packaged up into a map, and then it goes on to do the same for Python. Those 2 maps are then merged together into a big map that represents a complete row in the synthetic data table. Let's make some space by hiding the arguments to those distributions. Instead of using let to bind the results of expressions to symbols in this program, we use a different construct called let_traced. Let_traced behaves like let, but in addition it also records the value being bound in a data structure called a trace. If we execute the program, in addition to getting back a return value, we also get back that trace. Here's the return value in the trace that we get after executing the program once. And here's the return value in the trace that we get back after executing the program again. Many of InferenceQL's internal API functions accept these traces. In particular, one of the functions accepts a program and a trace and runs that program, forcing it to sample any values that are present in the trace. This is how the given clause you saw earlier is implemented. You can also pass the trace to a different API function to calculate how likely it was that the program sampled those particular values. But we'll save that for another talk. And now we've arrived at one of the ways in which we hope InferenceQL might be able to help reduce algorithmic bias. Machine learning models perform poorly on populations when they're not well represented in the training data, and the real-world consequences when they do can be severe. For instance, if we were to train an AI model on the 2021 Stack Overflow Developer Survey, it would likely perform poorly on non-binary people because there are so few of them in the dataset. But experiments have shown that adding synthetically generated records to training data can help ameliorate this problem. Gretel.ai, a synthetic data startup, found that they could improve the accuracy of classification algorithms by adding synthetic data for underrepresented groups to the training dataset. Finally, let's explore one more way we could possibly reduce algorithmic bias in machine learning models. Another way bias can creep into models is if the dataset itself has evidence of real-world bias, as this one does. Since these automatically synthesized probabilistic programs can be edited after the fact, what would happen if we simply changed one such that it changed the one we saw before, such that it generates salary independently from gender? We aren't going to change the clusters, we're just going to extract out the logic for sampling salary from the logic that samples gender. So here's the program before making that change. On the right, we have a jitter plot where the y-axis is gender and the x-axis is salary. And as before, the black dots are real data from the survey and the orange dots are synthetic data. Now here's the program after making the change with its corresponding jitter plot. Now I'm going to flip back and forth quickly between these 2 slides so you can see the difference in the simulated values coming out of this probabilistic program in the plot on the right. Because we decoupled salary from gender, women and non-binary people are now simulated with higher salaries than they were before, even if the univariate distribution of salaries is unchanged. Could we reduce algorithmic bias by making these kinds of changes before feeding synthetic data into machine learning models? It would be interesting to find out. Now we'll talk a little bit about growth. We think InferenceQL shows a lot of potential, and it would have been hard to get this far with such a small team if it had been implemented in a less powerful, less expressive programming language. Because Clojure can target both the JVM and JavaScript, we can embed InferenceQL synthetic data generators as jars and JavaScript bundles, and deploy them within JVM data pipelines and in interactive browser-based applications where significant fractions of the world's sensitive data already resides. Clojure's immutable persistent data structures make it easy to scale InferenceQL queries via parallelization. Structural sharing makes it possible to persist the full history of changes made to models during the model synthesis process. Because Clojure is a hosted language, we've been able to interoperate easily with libraries that are written in more mainstream programming languages, such as the API for GPT-3. We'll show you a demo of that in a moment. Finally, the probabilistic programming language we showed you today is implemented in Clojure via macros. Not only has this made the implementation of that language easier than it otherwise would have been, but it also conveys to that language the same benefits that Clojure enjoys by being hosted on the JVM, among them access to a high-performance JIT and access to Java's massive library ecosystem. In terms of giving back to the Clojure community, one thing we'd like to do is start adding Clojure script support to some of Clojure's data science libraries. This isn't a common workflow today, but we think that there are some very interesting applications that could be unlocked if more of those libraries were cross-platform. Secondly, InferenceQL has an open source license, but we're still preparing for its public release. In the meantime, if you have an interesting application in mind and would like to help us test the software prior to launch, please get in touch with us. Work has also begun on a new implementation of the Gen probabilistic programming language targeting Clojure, which will also be open source. And finally, just as Babashka made it possible to write fast-starting scripts in Clojure, we hope that InferenceQL will make it possible to use Clojure in a different, new and growing domain, synthetic data generators.
Let's zoom out and look at the bigger picture. Let's ask ourselves, what if a significant fraction of databases came equipped with an AI domain expert based on InferenceQL? Our research has shown it's possible to go from time series data, panel data, cross-sectional data, and even relational data to probabilistic programs that we can query not just to generate synthetic data, as you've seen, but to answer a much broader range of questions in data science. Zane is going to show you one such example so you can get a sense of how far we think Clojure might be able to grow if InferenceQL proves successful.
Now, we chose to base InferenceQL's query language on SQL in order to maximize InferenceQL's reach. Because SQL queries are essentially structured English, simple queries can be understood at a high level even by people who don't understand the language. We want InferenceQL queries to, as much as possible, be readable by everyone from government officials to decision makers at companies and nonprofits to the general public. But recent research being led by Joao Lula at the MIT Probabilistic Computing Project is beginning to suggest that we might be able to make reading and writing complex InferenceQL queries accessible to everyone without training. What we're about to demo is a research prototype that integrates the InferenceQL query engine with a GPT-3 model that's been fed a corpus of InferenceQL's documentation and example queries. I think the result is pretty striking. Users can enter questions in plain English, and those questions are translated by GPT-3 into InferenceQL queries, which are then executed against InferenceQL's automatically learned models. You can ask simple questions like, show me 5 rows from the data, or even complex questions like, show me people who are probably underpaid, given their background and experience. How would the world be different if anyone could ask, in their native language, questions about evidence of inequality in public data sets and get fast, accurate, auditable answers? We hope to find out. Thank you.